Welcome to this video lecture series on transportation engineering. In this session, we shall discuss on the radius of the relative stiffness and the temperature stresses and its equations. So first is the radius of the relative stiffness. So certain degree of resistance of the slab deflection which will be offered by the subgrade. So in this case, the subgrade deformation, it is the same as that of the slab deflection, because if there is a deflection into the subgrade which will lead consecutively to the deformation of the slab. Hence the slab deflection, it is a direct measurement of the magnitude of the subgrade pressure. So this pressure deformation characteristics of the rigid pavement led by Westergaard in order to define the term radius of the relative stiffness L in centimeter, which is given by the equation L equals to E into H cube upon 12 into K in the bracket 1 minus mu square bracket raised to 1 by 4, where L, it is the radius of the relative stiffness in centimeter, H is the slab thickness in centimeter, E is the modulus of elasticity of the cement concrete in kg per centimeter square, mu is the Poisson's ratio for concrete generally taken as 0.15, K is the modulus of the subgrade reaction in kg per centimeter cube. Next, the equivalent radius of the resisting section. So when the interior point, it is loaded only a small area of the pavement, it is resisting to the bending moment of the plate. So according to Westergaard, the equivalent radius of the resisting section, it is approximated in terms of the radius of the load distribution and the slab thickness. So here B, it will be equals to under root of 1.6 into A square plus S square minus 0.675 into H if A, it is less than 1.724 into H, where B, it is the equivalent radius of the resisting section in centimeter, H is the slab thickness in centimeter, A is the radius of the wheel load distribution in centimeters. So when the value of A, it is greater than 1.724 into H, then the equivalent radius of the resisting section, it is taken as equal to the radius of the wheel load distribution, that is B, it will be equal to A. Next is the temperature stresses. So the two types of stresses, they are produced due to the temperature variation in the concrete pavements. First is the wrapping stress, which is due to the temperature difference in between the top and the bottom of the pavement, which will be a result of the daily variation in the temperature at the given location. And secondly is the frictional stress, which will be due to the overall increase or decrease in the temperature of the pavement slab as a result of the seasonal variation in the temperature at the given location. So the wrapping stresses at the interior STI, they are given as STI equals to E into small e multiplied by T upon 2 in the bracket Cx plus mu into Cy upon 1 minus mu square. Again, wrapping stresses at the edge STE, it is given by STE equals to Cx into E multiplied by small e into T upon 2, or Cy multiplied by E into T upon 2. Here the wrapping stress at the edge, it should be chosen the greater of the two. And lastly, the wrapping stresses at the corner STC, it is given by STC equals to E into T upon 3 multiplied by 1 minus mu multiplied by under root of A upon L. It should be noted that at certain times the notification for the wrapping stresses, rather than taking it as ST, also it can be given it by sigma Ti, sigma Te and sigma Tc. So both these equations will give you the same results, but there is just the change of the notification. Where E is the modulus of elasticity of the concrete, small e, it is the thermal coefficient of the concrete per degree centigrade. Next, T, it is the temperature differential between the top and the bottom of the slab. Mu is the Poisson's ratio of the cement concrete. Cx, it is the coefficient in the direction x, which depends upon the ratio Lx upon L, and Cy is the coefficient of the direction y, which depends upon the ratio Ly upon L, where L, it is the radius of the relative stiffness, and Lx, it is the length of the transverse joint in centimeter, whereas Ly, it is the length of the longitudinal joint in centimeters. Next is the frictional stresses. The frictional stresses, they can be calculated as SF equals to WLC into F upon 2 into 10 raised to power 4, where SF, it is a stress developed due to the interface friction in the cement concrete pavement per unit area in kg per centimeter square. W will be the unit weight of the concrete, which will be about 2400 kg per centimeter square. F, it is the coefficient of friction at the interface, maximum value of 1.5. LC is the spacing between the contraction joint, that is the slab length in meters, and B is the slab width. Next is the combination of the stresses. So the cumulative effect of the different stresses, they will give rise to the three critical cases. First, in the summer midday, the critical stress is for the edge region, which will be given by sigma critical will be equals to sigma E plus STE minus SF. Second, for the winter midday, the critical combination of the stress for the edge region will be given by sigma critical equals to sigma E plus STE plus SF. And lastly, at the midnight, the critical combination of the stresses is for the corner given by the sigma critical, that is sigma C plus STC. So all these three critical cases, they should be considered for the cumulative effect or the combination of stresses. Next is for the design of the dowel bars. So for the purpose of the dowel bar is to effectively transfer the load between the two concrete slabs and to keep the two slabs in the same height, or to keep them at uniformity. So the dowel bars, they are provided in the direction which is longitudinal, and the design considerations are the mild steel, they should have the mild steel rounded bars, and second, they are bonded on one side and free on the another. So the Bradbury's analysis, it gives the load transfer capacity of a single dowel bar in shear, bending and bearing as follows. So the Bradbury, he has put forward certain equations. First is PS equals to 0.785 d square into Fs. Second, PF equals to 2 into d cube into FF upon LD plus 8.8 into delta, and PB equals to FB multiplied by LD square into D upon 12.5 into LD plus 1.5 into delta, wherein P is the load transfer capacity of a single dowel bar in shear S, bending F and bearing B. D is the diameter of the bar in centimeter. LD is the length of the embedment of the dowel bar in centimeter, and it is joint. Then FS, FB and FB are the permissible stresses in shear, bending and bearing of the dowel bar in kg per centimeter square. Next is the tie bar. So in contrast to the dowel bar, the tie bars are not required or used, or they do not load transfer devices. They are not used as a load transfer devices, but they serve as a means in order to tie the two slabs together. Hence, these tie bars, they must be deformed or hooked and must be firmly anchored to the concrete to function properly. So there are smaller, these tie bars, they are smaller than that of the dowel bars, and they are placed at the large intervals as compared to the dowel bars. They are provided across the longitudinal joints. So for the design of the tie bars, the first step is in regards to the diameter and the spacing. So the diameter and the spacing of the first is first found out by equating the total subgrade friction to the total tensile stress for a unit length, that is 1 meter. Hence, the area of the steel per 1 meter in centimeter square is given by AS equals to B into H into W into F upon 100 into S, wherein B is the width of the pavement panel in meters, H is the depth of the pavement in centimeter, W is the unit weight of the concrete, which is assumed to be taken as 2400 kg per centimeter square. F is the coefficient of friction, which is assumed to be taken as 1.5. Then SS is the allowable working tensile stress in the steel, which is assumed as 1750 kg per centimeter square, and we have to assume 0.8 to 1.5 centimeter bar for the design of the tie bars. Next, the length of the tie bar. So for the length of the tie bar, it is taken as twice the length needed to develop the bond stress equal to the working tensile stress, and it is given by LT equals to D into SS upon 2 into SB, where D it is the diameter of the bar, SS is the allowable tensile stress in kg per centimeter square, and SB it is the allowable bond stress and can be assumed for the plain and deformed bars respectively as 17:5 and 24:6 in kg per centimeter square. So the design guidelines for the rigid pavements as per the Indian Road Congress guidelines of 2015. First, we will have to consider the factors governing the design. Next, the axle load characteristics as discussed earlier. Then the wheelbase characteristics of the vehicle. Then the design period of the pavement. Next is the traffic consideration, followed by the temperature consideration where the pavement it has to be constructed, and lastly the embankment soil and characteristics of the subgrade and the sub base. So first case, the factors governing the design. So the various factors which will be governing the design of the pavement firstly will be the design period, to what actual period the rigid pavement it has to be constructed. Generally it is taken as 30 years. Second is the design of the commercial traffic volume. What actually will be the commercial volume of traffic or the vehicles which will be moving on that pavement. Next is the composition of the commercial traffic in terms of single, tandem, tridem, multiple axle load spectrums. So this grouping of the various vehicles into the axle loadings. Next, the tire pressures, followed by the lateral placement characteristics and the directional distribution of the traffic on the pavement, and lastly the strength and the foundation and the climatic condition existing on the site, because the characteristics of the type of strata available for the foundation on which the subgrade has to rest, it will have its influence on the selection of the entire material which will be used for the construction. At the same time, also it will influence on the total depth of the pavement, and the climatic conditions, they will again have its effect on the design that can be regarding the provision of the camber, the drainage, the sub drainage facilities to be provided for the pavement. Next is the axle load characteristics. So the legal axle load, it limits in India, they are 10.2 tons or 100 kilonewtons for a single axle, 19 tons or 186 kilonewton for a tandem axle, and 24 tons, that is 235 kilonewton for the tridem axles. But it has been observed that much heavier load it is carried over the national highways than the legal limits. So this actually causes to the deterioration or the settlement or the deflection in the roads earlier than as compared to the design period of the pavements. Next is the wheelbase characteristics. So the wheelbases of the trucks of the different modes, generally they range from 3.6 meter to more than 5 meters, whereas commonly used spacing of the transverse joints it is 4.5 meters. So in this particular way, the axle with the spacing of more than 4 to 5 meters will not contribute to the top down fatigue cracking. But however, if the actual spacing of the transverse joint it is different from 4 to 5 meter traffic estimation of the top down cracking, the damage it will be selected appropriately. The design period. The lifespan of a design of the rigid pavement it is generally considered to be taken as 30 years or more, I discussed earlier. But there are various factors like the traffic volume, uncertainty of the traffic growth rate, the capacity of the road, and the possibility of the augmentation of the capacity by widening. It should be considered during the design period calculations of a pavement. Next is the traffic consideration. So following points they are to be taken into account in the traffic consideration. First one is the design lane, and second is the design traffic. So for the design lane, the lane carrying maximum numbered heavy commercial vehicles is termed as a design lane, and each lane of a two-lane highway and the outer lane of the multi-lane highway they are being considered. Whereas for the design traffic, the average daily traffic should normally be based on the 7-day 24-hour count by the Indian Road Congress section 9, and as per the Indian Road Congress, the annual growth of the commercial vehicles it shall be a minimum of 5%. That means at each year at least there will be a growth of 5% in the use of the commercial vehicles. So in case of a new highway link where no traffic count data is available, then the data from the road of the similar classification and importance may be used to predict the design traffic intensity. So this data actually helps us wherever there is no data available to the similar sort of a road which is constructed in the earlier period. The same data it can be used for the design. And in case of a 4-lane and other multi-lane roads, divided highways, 25% of the total traffic in the direction of the predominant it may be taken into consideration for the design of the pavement. So whenever a 4-lane road or a multi-lane road it has to be constructed, then the 25% of the total traffic in the direction of the predominance it may be taken into consideration. So the cumulative number of the commercial vehicles during the design period it may be estimated from the following relation: C equals to 365 into A multiplied by 1 plus R into the bracket raised to N minus 1 upon R, where C equals to a cumulative number of the commercial vehicles during the design period. A is the initial number of the commercial vehicles per day in the year when the road is open for traffic. R is the annual rate of growth of the commercial traffic volume, and N is the design period in years. Next is the temperature consideration. So the temperature differential and the zero stresses temperature it is considered for the design of the rigid pavements. The embankment soil characteristics of the subbase and the subgrade and the subbase. So this is the last point as far as the design guidelines for the rigid pavement is concerned. So the CBR value, that is the California bearing ratio of the embankment soil placed below 500 mm is selected subgrade determined for estimating the effective CBR of the subgrade and the modulus of subgrade K value for the design. Then the nature of the embankment foundation strata, like the expansive clay, the marine clays, the black cotton soils, the soft clay, etc. It should be studied so as to take the measures in the design, and the relationship between the CBR and K values it gives the following table which can be used of the homogeneous soil subgrade. That means we have the values of the CBR and the key which will be used for the homogeneous soil subgrade mass. So the design steps for the rigid pavement as per the Indian Road Congress section 58 of the year 2050, amendments as per the year 2015 is: first, stipulate the design values for the various parameters. Second, go for the selection of the trial design thickness of the concrete pavement slabs, which will be followed by the determination to determine the repetition of the axial loads of the different magnitudes and different categories during the design life. Then we have to compute the proportions of the axial load repetitions operating during the day and the night time. Next is to estimate the axial load repetitions in the 6-hour period during the day. Then sixth step will be to estimate the axial load repetitions in the 6-hour period during the night time. Seventh step is to determine the flexural stresses at the edge caused by a single and a tandem axial loads. Eighth step is to determine the maximum flexural stress in the top surface of the pavement slab. Ninth step is to make the sum of the cumulative fatigue damage for the bottom up cracking and the top down cracking. So if this sum it is less than 1, then the pavement slab it is safe against the fatigue cracking. And lastly, to design the joint such as the contraction joint, construction joint, expansion joint and longitudinal joints, and then to go for the design of the tie bars for the longitudinal joints. So as far as the syllabus is concerned, at your B level only these design steps they are to be known. No actual design of the rigid pavement is being asked into the exam. Just you'll have to go through all these design steps and you should know what actually are the steps in order to design a rigid pavement. So with this we come to an end of unit 5. Thank you.